Okay, so welcome to the second day of the workshop. So this morning we have Professor Mathur to tell us about the difference between fuzzball and wormhole paradigms.
Okay, is the mic working? Okay, so yesterday we talked about the information puzzle and what the puzzle was. So today let us talk about what could be the solution of the puzzle. So let us just first begin by recalling what the puzzle was. And the puzzle had the following form. So let me just begin with first recall the puzzle. And the point was that if the black hole looks like this and all the mass in the black hole is at the center, then this region out here is just the vacuum. And if it is the vacuum, then you will actually get production of pairs here. And these two members of the pair together have energy 0, so they don't cost any energy, and this process can happen. And then if you look at the state of this pair, it's an entangled state. And you can write the entangled state in many ways. Doesn't matter how you write it. Entangled state just means that the state of this and the state of this are not simply multiplied together. It is something times something plus something times something plus something times something. There are many terms in it. So if you write the state of the pair, then it has the form. Let me just put two terms for simplicity. It looks like we can call the states 0 and 1. It doesn't matter what the states are. So 0 for the in particle, 0 for the out particle, and the other state you can call it 1 for the in particle, 1 for the out particle. So this description is a little schematic. The 0 and 1 can correspond to electron versus positron, or spin up versus spin down, or it could correspond to there being occupation number 0 or occupation number 1, like we finally found in the Hawking calculation. But in any case, the state is not something times something. It is something times something plus something times something, which means the whole thing is entangled. So when you have an entangled state like that, then each time you produce a pair, the entanglement actually keeps going up. And this is what is called the page curve. So if you plot the entanglement, that is called S for entropy, but it's an entanglement entropy. So there's an ENT down here. As a function of time, then it just keeps growing monotonically up. And then the puzzle itself was that when in the end you have all the radiated quantum, and suppose this black hole completely vanishes, then you are left with all these particles whose state is entangled, but their entanglement partner has disappeared. So then they don't have any state at all. So let me write no state and put question marks there, because that's a violation of quantum mechanics. And so that was the puzzle. So now our question was, what is the solution to the puzzle? And so, of course, the most obvious solution was that instead of completely evaporating, you get left with a tiny remnant, because once something becomes as small as the Planck scale, you can say you don't really know what is going on. So that's solution 1. So that's called the remnant solution. So let's call that solution A. And in that case, you have a problem, though, because the remnant must have infinite degeneracy. There are infinitely many states possible in this small, tiny object, which has size a mass of just Planck mass. And the size is Planck length. And even though you can make models like that, ad hoc models which have remnants like that, you can't have it in string theory because of ADS safety duality. So let me just write not in string theory. So because I'm mostly focusing on string theory as being a good theory of quantum gravity, which we understand sort of completely, for the moment, I would say that remnants is not the direction you might want to go. So if remnants are not there, what else is possible? So let's talk a little bit more about the page curve. As we said, this is the object which is called the page curve. So this is the page curve you find for a black hole. So let me write this for black hole. But let's just compare this with what's the page curve for a normal body. So let's ask what is the page curve for a normal body. And that page curve looks like this. So again, here is time, here is the entanglement. The page curve goes up, but then it comes down to zero. So let's just try to understand why that is the case, because once we understand that, we'll try to understand what the solution to the puzzle might actually look like. So why does the page curve for a normal body first go up and then come down? So let's make a toy model. Suppose here is a piece of coal which is made from atoms, and the coal is going to burn, and in the end, the coal is going to go away. So that's my piece of coal. So in the end, how does the coal emit anything? These electrons here are all in excited states, maybe the n equals 2 states. And when the state comes down, it will emit a photon. So first, let me just make a simple model, but I have only 2 atoms in the coal. Okay. So this is when I start. And so at the start, far outside here, there is nothing. If there's nothing, there's obviously no entanglement. There's nothing to entangle between here and here. So the curve starts at 0. So that's over here. Then after some time, what happens is one of the atoms will come down to the ground state. I'll draw it like that. It comes down to the ground state and it emits a particle, a photon. So now when the photon is emitted, we can just make a toy model where the photon has 2 spins. So suppose the atom started off with no spin, no angular momentum, then the full state of the final, this pair can be down times up minus up times down. If this was a singlet, when it breaks into 2 pieces, together they must have 0 angular momentum. So you could imagine the whole thing makes this minus this. And that's exactly the kind of entangled state we were talking about. Up, down, minus, down, up. That's a singlet. So now you can see that this guy is entangled with this. This photon doesn't have a definite spin state. It is up if this is down. It is down if this guy is up. So the entanglement between here and here has increased. And so we are up here on this curve after one photon has been emitted. So after some time, the other guy also emits a photon. So now I have 2 photons here. This is the outside. And this photon is entangled with this guy, and this photon is entangled with this guy. And so now the entanglement is even more. There are 4 possible states. This could be up or down, this could be up or down, and this is the partner state. So there are 4 terms in a sum like this. And so the entanglement has reached a very high value. But I'm trying to make a model where the coal completely evaporates away. So now I will ask that this thing should also go away. So once when a coal stops burning, you just have some ash left back, but the ash can also just fly out. So I'll make the ash go away so nothing is left. So at the next step, I'll try to maybe just squeeze it in here. One of the ash pieces is left here, and at infinity, I have 1, 2, and one of the pieces of ash. Okay. So if you go to that step, then you find what is the entanglement. This guy is still entangled with this guy, but this is just entangled with this. So if you compute the entanglement of whatever is outside with whatever is left behind, you only have the entanglement of here to here, and that's not such a big amount, so I've actually come back here. And then at the last step, this guy also goes out. So at the last step, I'll draw it here. I have nothing left here. I have 1 guy, 2 guys, 1 piece of ash, another piece of ash. This is entangled with this, and this is entangled with this. But nothing is entangled with what is left behind. So the entanglement of the radiation, this whole thing is now called radiation. It's what got emitted with whatever is left behind has come down to 0. So that's the normal process. And everybody has that kind of process. If you burn a piece of coal or piece of paper, first the guy goes up and then it comes down. So this is what we call the page curve of a normal body. So what is the difference between that one and this one? How come there it went up and came down, and here it kept going up? That's what we really want to understand. And the difference in the 2 cases comes from the following fact, that here each time you produced a new particle of radiation, something going out, you pulled out the 2 particles which of the entangled pair out of the vacuum. So they came out of the vacuum. When you pull something out of the vacuum has no spin or anything of its own. So these 2 guys are always entangled with each other. So every time you produce something from the vacuum, the entanglement is always going to go up. What happens here is that in the beginning, you pull the photon out of whatever was here, so the entanglement went up. But after some time, the other member of the pair, it also came out. And so that's how the entanglement went down. Because if both the photon and the atom are both outside, well, they're not entangled with anything left behind. They're only entangled with each other. Okay? So this is the problem. As long as you keep getting the particles out of the vacuum, the guy which falls inside, only if this guy actually comes out, then the entanglement can go down. But this guy is never coming out. So then you could ask, if this guy is never coming out, how does the whole black hole vanish? Well, that's what we said right when we started the discussion yesterday. Even though this thing has a big mass m, the initial star which collapsed to make the black hole, and there are all these other electrons and positrons which fell inside, so the mass looks to be even more. But the gravitational attraction was a negative sign, minus gmm over r, so the net energy went to zero. And if you believe that when you have zero energy, you have just the one state, the vacuum, it's not clear how, but somehow the guy has to vanish completely. And if it vanishes completely, then you're left in this problem where the entanglement has gone up, but there is nothing left behind. So the whole difference was that if you ever have a horizon, a smooth horizon like this with a vacuum, you will always have a curve going up. Well, if you have a normal body like a piece of coal, so which I draw like this, and it is radiating stuff, then the page curve will have no problem. And that's because the radiation which is being emitted is sort of being emitted from some object, and that object also has to come out to infinity before the guy can completely burn away. So this is just a way of making the puzzle clearer in the language of the page curve. So when you hear people saying the page curve of a black hole, page curve of a normal body, the solution to the puzzle, if you want to say it in terms of the page curve, is that this page curve should change over and become like this kind of page curve. So the simplest way to solve the problem would be that the black hole, instead of having this kind of picture, should somehow change to something which looks like a normal body, like a piece of coal. Namely, this guy had a horizon, and a horizon is something which is defined by the fact that on the two sides of the horizon, here the energy is negative energy, and here the energy is positive. So that's what the meaning of the horizon, that if you go inside a horizon, the gravity is so strong that a particle can have negative energy. That is what gives rise to the instability, and then the problem will just follow, because the vacuum will just create the pairs, and you will have the instability. But suppose the object has no horizon, so let me write here, no horizon, and that means the energy is actually positive everywhere. This is positive E. So E is positive everywhere. So every particle, any test particle placed anywhere only has positive energy, then this problem will not happen. Okay, then it can still radiate, but radiates like a piece of coal. Like this guy is going to radiate by becoming a smaller piece of coal, and something comes out. There's nothing wrong with that. That's how a piece of coal burns. But here, even though it's true the black hole becomes smaller, it actually, in some sense, becomes more complicated because there are more guys sitting inside it. And so in some sense, there is more stuff here when the radiation comes out. In the normal body, when stuff comes out, there's really less stuff here. There are less atoms left behind. But here there is more stuff, the original matter plus all the negative pairs, and so things are getting more complicated, and that's obviously going to be problematic. That gives this kind of a page curve, and normal bodies have this kind of a page curve. Okay, so our question is, can the black hole really be like this? If the black hole was like this, there's going to be no problem. And what I'm going to argue is that from what we are seeing right now in string theory, that seems to be the solution of the problem, that if you actually try to make a black hole in string theory, you don't actually get something like this. You don't find all the mass going to the center and then just leaving a vacuum outside. You seem to be getting something like this, which has got just stuff everywhere. There's no horizon. So the most important aspect of that would be there is no place where you can place a test particle and actually get negative energy. Okay. So this kind of object, we'll come to it in a minute. I'm not going there yet. But when we get that, this is what is called a fuzzball. So let's see why somebody, so of course, in one sense, that looks like a simple solution to the problem. Well, if the black holes are like this, every black hole is like a star, and it's a star made of some kind of strings and brains or whatever you have in string theory. So just like some stars are made of atoms, some stars are made of neutrons, some stars could be made of strings, and those are the ones we call black holes, and there's never any puzzle. So that's the actual fuzzball resolution of the paradox. But so why were people not immediately happy with that? Well, immediately, if you look at it, you find this looks a little confusing, because this picture of the black hole really came from classical physics. And if you think of quantum gravity trying to change this physics in some way, you might think that quantum gravity only acts on the scale of the Planck length, and the Planck length is really very small. It's 10 to the minus 33 centimeters. So people were willing to imagine that if you took the classical black hole, which has all the mass in the center, perhaps you could make some kind of a change where this thing becomes maybe a little bit smeared out to Planck length. But they couldn't imagine that it would change all the way up to the horizon, because all the way up to the horizon, well, that distance for a solar mass black hole is 3 kilometers. And could quantum gravity effects actually change something all the way out to 3 kilometers, because the natural length scale on the problem is 10 to the minus 33 centimeters. So it's okay to worry about that at first sight, but this itself is actually not a good argument to worry about. So let me tell you why this is not the real worry. There is another worry which is a real worry, which actually has a very interesting and much deeper solution. But this which looks the worry at first sight is not the real problem. So let's see why this is not the real problem. This is not a good argument by itself. So what actually happens in string theory is that you're trying to make a black hole. So let me just try to say in roughly what does happen. So in string theory, you just have some strings and some branes and stuff like that. And if you make a bound state of them, well, that will be the black hole. Because after all, a black hole must be something which you take from the objects of the theory and you put a lot of mass together, whatever it makes is going to be a black hole. So when you do that, you have to find what is the size of the object. That's what we are asking. Is it going to be something of size Planck length? Or is it going to be something which is as big as the horizon? That's the question. So what is the size of the bound state? Now, string theory also has only one fundamental length. You can call it the Planck length. Sometimes people call it the string length. But the two are connected by a fixed ratio, just a string coupling, which is just a small number, like you can think of it as 0.1. So you can think of Planck length and string length as being both microscopic lengths. Whether you talk in terms of Planck length being fundamental or string length, it doesn't really matter. It's a fixed length, so it can never go all the way out to the horizon of a black hole, because that can be as big as you want to make it. Okay? But what is the size of a bound state? So if we to make a big black hole, you have to take, let's say, n different branes together. And the number n will be much bigger than 1. So now you have to ask, even though the fundamental scale in the problem, which you can make out of the constants c, h bar, and g, the only length scale you can make out of them is Planck length. You actually now have 4 numbers in the problem. You have c, h bar, g, and n. And now you have to ask, what is the scale of the bound state? How does it depend upon n? One possibility is it remains Planck length. It doesn't depend on n. And there are examples you can give of that. If you, for example, want to make a Bose condensate. So you put some bosons all in one spot to make a bound state, but you can put many bosons on top of each other. So then if one boson had a wavelength of some lambda, you can put 1,000,000 bosons, the whole bound state still has size lambda. Okay, so that's an example where the size of the bound state does not depend upon n, so then it could look like this. Okay, but let's look at other cases. There are other possibilities. This could be some power of n times Lp. What's the example we know of that situation? If you take the nucleus, you know, a nucleus is made of many nucleons, protons and neutrons, and they go into what is called hard sphere packing. They don't overlap. They're just like marbles, you put them around. So if you look at a nucleus, and the atomic number A is the number of nucleons, the A, because you do hard sphere packing, the size of this, let's call the size of this R, the R goes like A to the 1/3. So here A is your n, so it's going like n to the 1/3. So in fact, I should write this as n is the A, it's n to the 1/3 times in the units of Fermi, because size of one nucleon is about 1 Fermi. Okay? So in fact, the size of a bound state can definitely be any power of n times Lp. So a priori, there's no reason to know what that power is. And so when we actually started playing with string theory and finding out what is the state of the black hole, you find the answer is not like this. In all the cases you can actually manage to construct, the answer looks to be of this form. Okay? And then the question is, how much is alpha? Well, alpha is such the size of the object seems to be of the order of the horizon radius. So the bound state, so in this picture, if the size of the bound state is of the order of the horizon radius, you will actually get something like this, and that is your fuzzball. So just the fact that the effects are going all the way out to the horizon, and you say, hey, how can quantum gravity do this? That itself is not a good argument, because if you're putting a large number of particles, that large number can obviously figure in the size of the bound state. And in fact, when you try to make the states in string theory, it does seem to actually figure into the size of the bound states. And so the whole bound state can always have horizon size. If it really is that big, it becomes like a planet or a star, and you never have a horizon, and you actually have no problem. So all that we know from string theory in terms of actual constructions of black hole microstates seems to go in this direction. So you would say, okay, the problem is solved. This is what you actually have, and there is no difficulty with this. But there are two reasons to worry about it. One, which turns out to not be correct, but I'll talk a little bit about what direction people started worrying. And one which I said, well, this was not a good argument for worrying about scales. There is another question to worry about in terms of scales, which does seem to have an answer, but both the question and answer are important, and I'll come to that towards the end. Let me just stop here to see if there are any questions about what I said so far. Okay, so if that looks good, let's continue with this. Let me see what I had next on my agenda. So let's get a little bit more familiar with the scales of the problem. Scales of the black hole problem, of black hole evaporation. And in this discussion, the important thing will be how many particles does a black hole emit before it is completely gone? We haven't talked about any numbers right now. We just said if you make a black hole like this, it will emit one pair of particles, then maybe a second pair and a third pair, and the entanglement will keep going up. But how big is the number of pairs that you emit? So let me just write that question. How many particles are emitted? It will turn out to be a big number. And the next step in what started worrying people about all this will come from the fact that this number is very big. So let's at least learn something about how big that number is, or what are all the scales in the problem. So it's rather beautiful that there is only one scale in the whole black hole problem, and everything just comes from that one scale. So what is the one scale? The radius of this horizon, let's call it r. That's the radius of the horizon. And we know that we had r is of the order of gm over c square. So you remember how that came. If you take the mc square of a test mass here, the intrinsic energy was mc square, the gravitational energy was minus gmm over r, and if you make them equal to cancel, you'll get r of the order of gm by c square. Okay. So we'll put g equal to 1, c equal to 1, and then you can see that r is of the order of n. Okay. So these units are okay with everybody? G is 1, c is 1, so there's only one length scale in the problem, and that length scale is r, and r is 3 kilometers for a solar mass. So if m is m solar, then r is 3 kilometers. Okay. So now if you ask for the particles which are emitted from here, most of the emission for such a large black hole happens in particles which are the lightest particles. And the lightest particles are the massless particles. So let's just take a look at emission of photons. But you could equally well think of other massless particles like neutrinos, or you could think of gravitons or something like that being emitted. So if you look at photons, they're described by a wavelength lambda. And if you ask what is the wavelength of the emitted photon, there's only one length scale in the problem, so lambda will go like r. Okay. So there's another length scale like Planck length, but the Planck length doesn't come into the calculation we did yesterday because this was all coming from quantum fields on curved space. You remember we just had all these oscillators which just kept a field, and then the oscillators got separated and they broke up and you got entangled pairs. If you go through all that argument, quantum gravity doesn't really come in, so LP doesn't come in. There's no Planck length. And so if the other length scale cannot be used, then r is the only length scale, and the wavelength of the photon just comes out to be r. So if you want the energy of each photon, let me call it E of the photon, that will be 1 over r. My h bar is also 1. I should write that somewhere. Okay, so we know the energy of each photon. So we can already find the number of emitted photons. That's going to be the total mass of the black hole divided by the energy of each photon. And so that becomes m times r. But m itself was like r if I put g and c to 1. So this becomes like r square. And so if you just want to put all the units back in, if you put the g and so on, this number is actually r over L Planck whole square. Or if you want to write in terms of m or m Planck, you can write as m over m Planck the whole square. Okay, so you can already see that the number of photons which are being emitted, we should choose something for that number. Let's say n, number of photons. It is much, much bigger than 1, because if you take a big black hole, like a solar mass black hole, then m is 10 to the 33 grams. And you divide by 10 to the minus 5 grams, then you square it, it's like some 10 to the 80. So it's a huge number of photons, and that's the number of photons you are going to emit. Okay, so let's continue this. Let's write down all the other scales in the problem. So what else can you compute from this? you can find the time of evaporation. So how long does it take to evaporate? Well, for that you need to know what's the rate of emitting photons. And again, there's only one scale in the problem. So if this is this black hole with radius r, and the photons being emitted have this wavelength lambda, which is of the order of r, then the rate of emitting photons is such that when one photon traveling at speed of light sort of leaves, when this photon goes here, then the next photon is emitted. So there's no other scale in the problem. And so the interval between photons, delta t between emissions, is of the order of lambda. Again, c is 1. So if I write a length, it's the same as a time. But delta t then is of the order of lambda, which is of the order of r. There's only one scale. So you can also now find the total time of evaporation, the t for evaporation. It takes time of order r for each evaporation. And then you have the number of evaporations needed, the number of photons emitted is r square. So this times r square. So it's r cube. And so if you want to restore all the units back, you can write this as r cube over r over L Planck whole cube times t Planck. You can put in terms of Planck, the time is given in terms of Planck time, but then it's r cube. And what does r cube mean? You can make it in the correct units by taking always r over L Planck, because with these choices, L Planck was 1, and so that's the time of evaporation. Okay, so now we have all the numbers in here, but the only number which was really important for us was that the number of particles which are emitted is actually very, very large. Okay. So let's see how that matters and how it started affecting how people were thinking about the problem. But let me just wait again for a second to see if there are any questions on this estimates. Okay, so this is the issue I already touched on a little bit yesterday, and that was the issue of small corrections. And so some of the story involves the small corrections in more detail, so let me talk a little bit about that again. So if suppose somebody says they don't want the answer to be fuzzball, so you don't actually want the whole structure to change and the whole thing to become a fuzzball, then what is the actual alternative? And so as I was saying yesterday, people were looking at the following possibility. So let me just write here the word possibility. And the possibility was that if you take the black hole here and you make the pairs as before, so if you assume that everything is close to semi-classical physics, all the physics we were doing here, we call that semi-classical physics because we are using some quantum mechanics, but we are basically using the classical Schwarzschild background of the black hole, and then we're doing a little bit of quantum mechanics on it, so we can call that semi-classical. So suppose there was some small errors. Semi-classical is what we did in the calculation yesterday. But suppose we are actually close to semi-classical, which means any corrections to that are very small. So if we have this situation, then the state of the pair, psi pair, which we wrote down just up before, it had already been given the schematic form like this, was just made of some entangled pieces. But it could always have a small corrections, which I call delta psi. So to say that delta psi is small, we can say that the norm of the state delta psi is less than some epsilon, and epsilon is much less than 1. Okay? Yes?
This argument, locality came somewhere.
In which argument? In this argument up here?
Yeah.
So let me see where. So we haven't made an argument. What do you mean by the argument?
The fact that the theorem says you have delta psi, then change in the
Okay, that I will say. Good. I'm absolutely going to say that. So we didn't say any of the details of the theorem yesterday, but I will absolutely have to say that now. Yeah. So I was right now just stating what the small corrections question was, which was bothering people. But then when we state the answer to that question, then we will exactly have to answer this. But here, suppose just some state to the change to the state of the pair. So let's try to understand what that change means. What does it mean to say we'll make a small change to Hawking's argument? Well, the number of states which you have available at those energies are not too many, because here is the black hole, and suppose you're emitting a photon here, so this photon can be, either in the state 0 or the state 1. Either there is a photon or there's no photon. Okay, so, or you can go up to 2 photons, but this is simple enough. If I want to change the state of the pair, what does it look like? Let's try to write the example of a change. So if I make that change delta psi, just write a toy example of that. You could have 1 by root 2, and then you could add maybe 1 minus some, I'll put epsilon 1 times 0, 1 times 0, 2, and 1 plus epsilon 1 times 1, 1. So if epsilon 1 is small, can you see that this is a small correction to the state which I had written originally? So I can have a slightly bigger chance of of being in the state 1, 1, a slightly smaller chance of being in the state. Okay. So now you can see I can actually make rather complicated states for the entire system. What do I mean by very complicated states for the entire system? This is for one pair, but let's write down the state for two particles. So psi for two particles, if we call it capital psi, we tried to write that yesterday. What happens when you emit two particles? The two emissions are still independent, but these epsilons can actually sort of couple the two possible emissions. So let me try to write the state of this in some schematic way, and then the idea of small corrections becomes a little clearer. So suppose I write you a state like this. One and two means in and out. I just don't want to write in and out all the time. So one means in and two means out. Is that okay for everybody? This is in and this is out. Okay, so it sort of looks like this. And I have to write the other pair also. So I'll multiply this by, this is multiplied by 1 by root 2, 1 minus epsilon 1 prime. Well, epsilon 2, let's call it. For the second pair, O1, O2. So 1s and 2s are actually getting bad. We still call them in and out because I'm using 1 and 2 for the first and second pair, and that will become very confusing. But so this is for the first emission. So maybe I should use 1 for everything for the first emission. And this is again in and out. But this is for the second emission. So this is all for the second pair which is being emitted. Okay, so now I've actually written down the state with arbitrary corrections when two particles are emitted. If I didn't have any epsilon 1 or epsilon 2, this was the state of the first pair, this was the state of the second pair, but I have allowed some correction to this one and some correction to that one, but all the corrections are small, so epsilon mod is less than epsilon 2 mod is less than epsilon. Any epsilons I put for any emissions, I'll make all these epsilons, epsilon 1, epsilon 2, all of them less than some given amount of epsilon. But now you see, I could actually make little cross correlations between the particles because I can make epsilon 2 depend on what happened in the first step. So I could actually make something more complicated where if I actually had 0, 0 in the first step, then I actually had one value of epsilon 2. And if I had 1, 1 in the first step, I would have a different value of epsilon 2. Okay. Now that is really correlating all the particles. That's the state we really want. This is too simple because here you just made some independent change to every particle. But let's try to write down a state where each pair is influenced by what happened to the other pair. So that's what people are really worried about. There could be slight delicate correlations between the pairs, and then we could maybe change the whole problem. So let's try to write down that state where there are now correlations between pairs, not just independently making small changes. If we just do these kinds of small changes with small epsilons, I think everybody was clear that nothing important would happen to the problem. But now let's try to write down the state I really wanted to show you. And that would look like this. It's 1 by root 2. So the first state will be exactly the same as what I wrote. It's 1 minus epsilon 1. It can have a 0, 0. But then if the first step actually had a 0, 0, 0 in, 0 out, 1, then what happens to the second state has a 1 by, for the second pair, is 1 by root 2. And then I'll put 1 minus epsilon 2 times O in, O out of particle 2, 1 plus epsilon 2, 1 in, 1 out of particle 2. Okay. But if I actually had the other possibility here, the second part of the one that actually went to the other case that I did have a pair there, then I'll multiply it by 1 by root 2, and I'll do a different thing here. I'll call it epsilon 1, 2 tilde. That looks like a bit of a mess. So let me just say in words what we did. We said at the first step, you could either create 0, 0 or you could create 1, 1. We can slightly change the probabilities of that because of small corrections, but that's not the important point. The important point is if I got 0, 0 in the first step, at the next step I make small corrections, but the value of the correction, epsilon 2, is different from the value which I will use, epsilon 2 tilde, if at the first step I actually got 1, 1. So now what happens at the second step depends on what happened at the first step. But still all the epsilons are small, but all the particles are now cross-correlated. It's not like they're just separate independent pairs. Where does this effect come from like this? So we say we don't know. Okay, there could be some quantum gravity effect that magically does this, but schematically you could say this is the black hole, right? First you commit the first pair. So this was the particle 1 and its partner 1 out here. And when the second pair is being created, this pair near the horizon, even though this particle is deep inside and normally there's no connection from here to here, there's no normal way in classical physics, semi-classical physics to have any influence from here to here. There, light can't go from here to the horizon. You remember how the light cones used to go. But we can imagine some kind of process which is not in normal physics does make an influence at what is happening for the creation of the second pair from the nature of the first pair. So if this guy was a 0, it does something here. If it was a 1, it does something else there. We just imagine it because we don't know what it is. And that is what is encapsulated here. But so you would say, since you cannot actually go from inside the horizon up to the horizon by maintaining causality, why are we writing that? Well, we are saying this is sort of encoding the physics which we don't know, and maybe there are magical things happening in the full quantum gravity theory. As long as they are small, you can't really complain. And that actually sounds reasonable. Okay. But now let us see how many such corrections there are. Because you can see there are lots of places. If you keep only the ones from every bracket, you get Hawking's answer. If you look at the terms which have the epsilons in them, well, those are corrections to Hawking. But the point is the number of terms like that is growing very rapidly because you could take the first correction from here and there's some term from here and some term from here. The number of terms which actually have any epsilon in them, if you do n of these steps, if you do n emissions, the number of correction terms which have some power of epsilon, it goes like 2 to the n. Okay, so it's exponentially large. Of course, some of those terms have many epsilons in them, so they are very small. But because there are so many correction terms, people started thinking, well, we don't know any solution to the puzzle, and the puzzle is so clear and so robust, and we have to solve that puzzle. And as we said in string theory, we can't even have remnants, so that solution is not allowed. So maybe the only solution allowed to us is that Hawking's original calculation just doesn't work because it was a leading order effect. So this was the argument then. So Hawking did leading order, which means you just keep all the terms with epsilon without the epsilon, and that's all he got. But then there are subleading effects, subleading terms, which are small, but there are many of them. Little bit reminds me of the kind of thing that Pimming was also having, though it's a different situation. But if you have many small things, they can change what is going on, right? And so the worry was that even though epsilon is much, much less than 1, the number of terms you emit, n, I think we call it little n there. Little n, the number of photons you emit. The little n is much bigger than 1. And if epsilon times the number of terms 2 to the n, if this number is still less than of order 1, okay? Sorry, if this number can easily be bigger than order 1. And if that's what happens, then maybe these corrections become very important. And if they become very important, then Hawking's leading order answer will not work. So what does it mean by saying it will not work? We now have to go and compute the page curve. So what we have to do is, we have to go back and say that now the full state of all the particles at some stage, there are all these guys which fell inside the hole, there are all these guys outside, and now everybody was entangled like this. This guy with his own partner, this with his own partner. That was Hawking's leading order thing, everyone entangled with their own partner, but there are now a lot of cross connections also. This guy has a little bit something to do with here, this guy has something to do with here, this guy has something to do with that guy. Those are all the other terms, the small epsilon terms. So they're all there. So we now have to again look at the outside entangled with the inside, and now the dotted lines, which are the small terms, can actually make some correction to the answer. And if we now try to plot the page curve, This is my entanglement, and this is time. In the beginning, when there are only a few particles, then there are only a few terms there, like I wrote 2 terms up there. And if the epsilon is small, obviously there won't be much difference. If the Hawking answer was going like this answer will be also close to that. But once I get to many, many terms, all these, even the Hawking answer was going like this. Once I take all the small corrections into account, maybe it actually goes like this. I'll put question mark because that's just a maybe, but it will actually go down like this. Now, if that happened, then you can be actually very happy. Because then in the end, when the black hole is sort of gone and all these guys are left, then there is no entanglement. Suppose all this entanglement basically became 0. Then if this guy disappears, as we said, there is no problem. These guys will just have some entanglement with each other, and that's okay. Even in a piece of coal, the entanglements are with things with each other. That's how we describe the piece of coal. The photons were emitted with the atoms left behind and all this, all messy entanglements. But the point is, this entanglement will be gone. As long as there's no entanglement with what is left behind, there's just a well-defined state for this because it's a pure state, and you can write some state for the radiation, and there is no paradox. So this was the hope, and this was sort of looking like a natural solution to the puzzle. And you can see this is very different from the fuzzball resolution of the puzzle because we're not changing the entire structure of the black hole. We're just saying the small corrections, but otherwise it's basically like semi-classical physics. So it certainly sounds very reasonable and sounds very interesting. But one thing which people never sat down to do was to check if it was true. So what do you mean by that? What that means is, suppose you choose some values of the epsilons and try to write out that whole thing. Okay, just take 10 particles, choose some value of epsilon, epsilon 1 tilde, epsilon 2 tilde. Try to make a toy model. It doesn't have to be true, but you just put some numbers and see if by choosing some epsilons with the appropriate signs and whatever, can you really make the page curve come down? Okay, if you can make one model like that, then who knows, quantum gravity may do something like that, and then it will come down. If you could make some choice of epsilon which will make it come down like that, then it would be okay. But it turns out that you cannot do that. So the small correction theorem basically says that, so the mathematics of the small correction theorem is just this. It says if you try to write down these things with any choices of epsilon, okay, and you can, all the epsilon just have to be bounded by this little epsilon, right? All the epsilons are bounded by some number epsilon. And then you have to find how much does the entanglement entropy decrease, and you can make it decrease a little bit by choosing the epsilons appropriately. But the whole answer to the small correction theorem is you can't decrease it too much. And so the amount of decrease, that's what I wrote on the board yesterday, the amount of decrease on the entanglement at the end upon the total entanglement is bounded by 2 epsilon. So it depends on epsilon, but this does not depend on n. That's the important thing. So let me write that here, does not depend on n. If it also depended on n, suppose it was something like n times epsilon, then I could not make any valid argument because n is so big, the number of emitted photons is so big that the epsilon could be small and the correction could be still order 1, and then maybe the page curve could come down, and then one day when we find all those small quantum gravity corrections, they may again actually be in such appropriate delicate way that the whole thing comes down. Then we would not have any puzzle to worry about. But this actually tells you the Hawking puzzle is actually very robust. Hawking did a leading order calculation. But if you look at all subleading terms, and you can write down any choice of epsilon, we didn't even try to choose the epsilons. Choose whatever you put, whatever you like. It's just a mathematical statement that any correction you make to those coefficients, where you can make any of the epsilons to depend anyway on the earlier epsilons, which just means that you can actually put into any numbers at all, because you don't know how they develop. Put any numbers there, the entanglement entropy will satisfy this theorem. Okay. So as far as this goes, we haven't even had to put any physics in it. This is just a mathematical statement of all kinds of states which you write down like that. You compute the entanglement of the outside out particles, all the O1, all the out, 1 out, 2 out, and so on, with a 1 in, 2 in, and it's just a theorem about what you can get out of all such states. Okay. Where does the physics come in? The physics comes in the fact of what we allowed in the states. Because if you look at these states, I said you could take the same states O in and O out, and 1 in and 1 out, and I only change the weightages a little bit. Now that's not the only thing I can do. I can of course make slightly more general states. Right. Here I could have also added some amount of epsilon 2 double tilde times 1 in 0 out. Okay, you can also make a few more states. They're actually 2 in states and 2 out states, so you can make actually 4 states and so on. Okay, so you can do that, and it doesn't change anything. The theorem remains the same. Okay. So Where is the physics? What's the physical assumption going into this theorem? And the physical assumption is the following. When I write it down, you will see how it actually goes into the nature of the state which we wrote down. And the physical assumption is that if you have a black hole here and you are emitting something, you may be making a pair or doing something, and these are the guys you emitted in the stages before. Once something has been emitted and has gone very far, what does very far mean? Let's say this is a distance of 100 times the Schwarzschild radius. You can choose some distance, suppose it's gone very far. Then the state of this guy does not change anymore. A state does not get influenced by the black hole. So that is how normally if you take a piece of coal and you burn it and a photon goes out, once the photon has gone very far away, then the coal is not actually interacting with it anymore. So the coal is not trying to change the spin of the photon anymore once the photon has gone 1 mile away. So that is how normal bodies burn. So that's the assumption, that once something goes very far away, the state doesn't change depending on what is happening in the black hole. Where is that assumption in the expression that we wrote? In this expression, when we did, let's say, the emission of the second pair, it did depend on what happened in the previous pair. How can it depend on the previous pair? Because the next pair, when it is coming out, the previous guy was sitting in here, right? The previous emission partner was sitting here, and this guy could influence the horizon by some effect which we don't know. In class, normal physics doesn't happen because you have to go faster than light to go outside, but we allowed it to happen. So all this is allowed. But what we said we don't allow, and so this state here could depend on what happened in the previous step. But what we did not allow is that once the guy has gone out here, we didn't change the state of this at a later step. So the emission was still one by one. When we try to write what happens at the second step, we made it depend on what happened at the previous step. Those guys were inside. But we never said that the state of this out guy at the next step, once it has gone out, it can change once again. So that's sort of inbuilt into the way we write this. If something can depend on everything which is inside, then it just means that every emission which is happening can depend on all the previous guys, because it can depend on all the previous guys which were in here, and that can influence this. But once the guy has gone out, we're not changing that guy's state anymore. If that's your assumption, that's the same as saying there are no non-local effects. So it's the same way of saying no non-local effects. So if there are no non-local effects, then the most general state you can write down will be of this kind. You can certainly add things like that. Doesn't change anything. Okay, instead of 2 states, there'll be 4 states and so on. Okay, so but there are only a finite number of states in that region at that energy, so you can allow all of them. And so with that, you find that you get to this theorem. And where did I write that? Delta S over S is bounded by 2 epsilon, and so then the page curve will have to keep going up, and it cannot come down. Okay. So now with this, yes.
So shouldn't we consider also the states of the collapsing matter or the background, in the
states of who? The initial matter.
Yeah.
Yes, absolutely. So you're absolutely allowed to do that. So I just wasn't writing it here, but let me absolutely write that now. So here inside the black hole, the state of the initial matter, which I called M, that's also sitting in here. And the original members of the pair which came are also sitting in here. And all of them can be responsible for whatever change happens to the next pair which is being emitted. So that means when you choose these epsilons can depend upon not only the previous states of the matter, but also on what was in capital M. Absolutely, you should allow that, right? But I actually allowed you even more. I allowed you completely arbitrary epsilons. And that's why I didn't have to actually say it depends on this or depends on that. The point is, as long as the correction at the horizon remains almost normal, the only thing I'm forced to have is that the state has to be at leading order, where I keep the ones, 0, 0, plus 1, 1. At subleading order, what the epsilon is will depend on all the things you say. But it doesn't matter, the theorem allows all of it.
Beyond what you wrote down, it wouldn't change the theorem. I mean, here
so let's try to write down the tensor. Let's try to write down what tensor what you mean, and then I'll understand better. So actually, so let's see what we wrote down. At the first stage, if I have only one emission, the state is, did I rub it out? It's just 1 minus epsilon 1, 0, 0, and then 1 plus epsilon 1, 1, 1, it already has a small correction. So with only one emission, that's the most general thing I could write down. Okay, and this epsilon 1, at this stage, there's no other particle in the hole. Let me just clean up my picture. There's no other particle in the hole. There's only M, and this is the first emission. This is one in and one out. And the effect of this epsilon 1, it can only depend on M. And that's why there's an epsilon 1. Okay. So that's it. When I come to the next emission, I have allowed you to achieve the most general tensor product. Let's see how that is. The most general tensor product is like this. If the initial state had two pieces, it was this plus this. When the next state comes in, if this goes with something for the next particle, and this goes with something else for the next particle, it is actually the most general state allowed. I just wrote it in terms of brackets, like I multiplied this with the bracket. But if you open out the brackets, it's important this is the most general tensor product you can write down. So I didn't try to factorize it or take it. So that's what I wrote before, which I rubbed out, right? That if you just write the first thing is completely factored from the second, that doesn't have the correlations. But you can't write anything with more correlations than this. This is already fully general. The question back there? Anybody? Yeah. Good. So no, absolutely. So this effect is never exactly zero, right? If that's what you're saying, even a photon very far away. So all we are saying is that once the photons are emitted, it's true that spins can still keep getting influenced a little bit by the black hole because all effects may fall off like 1 over r square or 1 over r cube. Okay. But those effects, we are saying that those effects are so small, we are assuming, are small enough to not change the S entanglement that you are computing. Okay. Yeah, I think that is. Yeah, I think that you can, if you know the effects are order 1 by r square, it is true, and you can prove that because there you at least know what they are, right? So if you put down 1 by r, you know what they are. What was happening from quantum gravity in the black hole, we didn't know anything about them, so we just said they are bounded by some epsilon, but we have no idea what they are. But in the long distance thing, you can actually check it because you can check it for a piece of coal. You emit a photon from a piece of coal. Electromagnetism also falls like 1 by r square. And then you ask, how does the entanglement for the photons with the coal? And you draw the page curve. Does that depend on the interactions between the coal and the 1 by r square effect left with the outgoing photon? And you find that those are too small. Right? So it's the same effect here.
If you want to claim it's very small, I think you have to know what the equivalent effect on gravity or effect equivalent.
Okay, so let me slow down and try to understand the question. Give me 1 minute to slow down. Yeah, so I was going to think about the coal also. Let me just draw coal here. I was going to clean out the coal problem so that there is no air in the room or anything. When I say analogy to coal, I imagine there's no air or anything to decohere it. I simply have a coal emitting photons. Okay, so there's no other environment for me right now. It's just EPR. There's nothing new happening there. Standard textbook Griffith's quantum mechanics. Nothing new, and that gives rise to the normal page curve. And now we are saying this exactly the same thing for the black hole. You simply get, it's just normal EPR. Again, there's no decoherence or anything. You get the entangled pairs. But we're just asking the EPR entanglement value, how does it change with time? And all we are saying is that if you're getting Hawking process, the EPR entanglement value goes up linearly, while for the coal, the EPR entanglement value actually comes down. But the coming down was not because of decoherence. It was simply because the photon which got emitted, and it was entangled with the EPR entanglement was with the remaining atom. After some time, the remaining atom also goes out. And so the entanglement still remains EPR between the atom and the photon, but because they are both in the radiation region now, the entanglement with what is left behind is zero. And that's such a simple statement. That's why it comes down in the normal page curve. So nothing deep is happening here in terms of entanglement, or it's a standard EPR, standard quantum mechanics in both cases. No environment, no decoherence, nothing. It is just normal EPR. It's just a question of where is the entangled partner. In the black hole, the entangled partner fell inside and never came out. In the coal, the entanglement partner also came out. That was the only difference. Otherwise, whatever you use the word EPR to describe entanglements, always exactly just that. Right now, that's exactly the assumption, right? Yeah, exactly. So that's our input. When I say no non-local effects, I mean exactly that I'm putting as an input that nothing magically comes from here to there. If you say there's a tunneling or a wormhole that can take this electron and sort of magically put it here, my conclusion will change. Because then it will be exactly like the piece of coal where the atom inside also magically came out, right? So when we say there are no non-local effects, we just mean that if there was a black hole like out there very far away, then it cannot magically send something from inside it and it comes here. And that's why we talked about the length scales in the beginning, because the distance to which this radiation collects, it's actually a very long distance, because the time of evaporation went like r cube, right? So that because the photons move at the speed of light, this distance is also of the order of r cube. Now the Schwarzschild radius is order r. So anything order r, you can do anything you like. We are allowing all these kinds of crazy effects that something goes from here to here. We don't even know what those effects are, but we allowed them. We are simply saying that we are disallowing effects of order r cube, or to be more precise, we are saying that the effects to order r cube can be there, but they are very small. They'll fall off like 1 over r6 because the distance is r cube and they are 1 by r square effects. And we are saying that those effects we can compute and estimate and they are too small. But if somebody says, no, there are new non-local effects that actually go across the distance all the way r cube and they are important, it's a different assumption, and the small correction theorem had nothing to say.
What would such a non-local effect look like in terms of these pairs? What kind of states?
So the non-local effect would look like the following, that what we call O out is not just a state O out. In the emission, I could call the state O out at this step, but when I write the state at the next, okay, so I just have 2 steps here. When I write the state at the step 2, at step 1, I only had this plus this, right? At step 2, I have added what happened to the second pair. It depends on what happened to the first pair. But when I write this whole state for the second pair, I will change this number again. I will change this state O1 and I will change it to, let's say, O1 out. Okay, let me just change it to 1 out. The out guy, its spin changes. The first out guy, which is already sitting there at infinity.
The second guy comes and it changes what was already there.
No, not this second guy doesn't change it. It changed because of what was inside the hole. So that's very important. So let's try to write this more slowly. The first pair came out. That was the first step of entanglement, right? Then at the next step, this guy is inside, this guy was there, and this guy is there, and a new guy heads out. That's the next step. That's the state I wrote down. But at the same time, something else happens. This is not everything. Suppose this guy had some state 0. At the same time, the guy came out, that guy changes to a 1. Because nothing to do with this guy. It just changed to a 1. The following is always allowed. If this guy also came out,
the very fact that it is emitting a second photon changes the state of whatever came out earlier.
Yeah. Well, at the same time step, you sort of did that. Now, who is doing that? I'm not saying that. But at the same time step, you also change the state of the outside guy. It's not happening if that's different from saying the second guy also came out, and then these 2 guys interact with each other and exchange their spins. That is always possible, right? If you collect many photons, they can interact. But when they interact, they don't change their entanglement to what is here. When bodies interact with each other, it doesn't change the entanglement of what is here with here. So that's not the change we mean. What we mean is that the entanglement of this spin of the guy changed with what was here. The 1 became a 0 became a 1 by some non-local effect, which has nothing to do with interaction with this guy. So because you're actually reduced the entanglement, right? I can write anything. If it doesn't change the entanglement, it hasn't helped you. To change the entanglement, I need to just change the state of that guy without its interaction with. If it is because of interaction, the net entanglement of these 2 will not affect what is here. So when you work it out, it won't do anything for you. But you can, if you magically sort of do something from here to here and you flip the spin of that guy, then the theorem doesn't apply. But if one guy is radiated and then doesn't change, then that is it. You had a hand up back there for a long time. Did you have a question for me? No. Oh, it's just about that. Okay. Okay.
Hello. I'm confused about non-locality. What you say? Because you just consider two-level systems. So could I just say that I can just use Bayes inequalities violation to define your non-locality here?
Okay. Let me try to understand the question.
I'm confused about your non-localities definition. So could I just, because you consider two-level system and the violations, maximum violation of Bayes inequality is equivalent to the entanglement generation for two cubic size, for two levels case. So could I just use the Bayes inequality violation to understand your non-locality here?
Use the what violation?
Maximum inequality, yeah. Because you consider two-level system.
Yes, the two level is fine. I mean, that's just a toy model, but you could take anything. So let's stay with two level. That's good enough for me. So the Bell's inequality has nothing to do with this in the sense that if I'm assuming the rules of normal quantum mechanical two-level system, which is what I've assumed everywhere here, the Bell's inequality is already built in, because Bell's inequality only distinguishes a system with hidden variables from a system which has normal linear superposition.
Yes.
Right? So here I'm assuming everything is just normal linear superposition. So I'm not going to go outside that domain at any time. I'm simply writing down normal states which have normal linear superposition. So the Bell's inequality is always true for me.
Okay.
Yeah, it's always true. Yeah, I'm not going to touch that. But indeed, people have tried to fool around. There's a question back there. Yeah, people have tried to fool around with that also. But if you try to change quantum mechanics, then oh, you had a question before that. I'm sorry. Yes, I forgot that you had a hand up before. Yes, go ahead.
I just want to make sure I understand the proof of that inequality. So are you saying that you just write down this general corrected state and you compute the entanglement entropy, correction to the entanglement entropy, and you obtain that universal bound?
So, okay, I didn't try to give you the proof here, okay? But that's not quite how you do it. The way you actually do it is the following. So let me sketch a little bit of the proof. What you do is you find the entanglement after you've done n emissions. So suppose there is some value. We don't know what it is, but suppose there's some value. Then you try to compute what is S entanglement at step n plus 1. And then the inequality is that you find this is equal to S of n, S entanglement at step n, plus log 2. The log 2 is because at leading order, if you just kept the Hawking process, because one more pair was emitted, that added log 2. Okay? And then you find that if you just add one more pair, then this is the inequality. So you actually prove it step by step, that at each step, it's going to increase by log 2, and the corrections can reduce it a little bit, but only by a small amount. So the graph will always keep monotonically going up because of this is bigger than this. It can never turn over, so you can never have an Sn plus 1 less than Sn. Okay, it always keeps going up. And so how do you prove that? So the reason that is not so obvious is that to prove that you need this bizarre thing called the strong subadditivity of quantum entanglement entropy. And that's a relation which you can prove, but it has no obvious proof. It's a very somewhat complicated proof. Strong subadditivity relation. So it takes about 10 pages to prove. So it was done by Lieb and Ruskay, and so you can find it in the textbooks. But it is not an obvious thing to prove. Entropy. Okay. And so if you use that, then you can actually prove this. And I just wrote this, in terms of the total thing, but what you actually end up proving is this. So I didn't give the proof here, but that if you're interested, I can sit down and show you. Okay, there's a hand back there. Yes.
So you end up with this multi-particle entanglement, multipartite entanglement, but you write it in terms of like a bunch of bipartite at every step. That's basically what's going on in this small correction. Like at every step, your pairwise additions are being considered, but it's not like a bona fide, like 17-bit, highly correlated, strange correlated thing. Is that
no? Okay. It is actually highly correlated. What you're trying to do is not make it bipartite. The Hawking original thing was just made of individual pairs which are all bipartite correlated, right? The first guy was entangled with this guy, next guy with his own partner, next guy with his own partner. So that was the trivial one. Now here, because you're allowed all the epsilons, and each of the epsilons is completely independent, you can make epsilon 2 depend on what happened in the first step. Because when I make epsilon 2 not equal to epsilon 2 tilde, when you write this out, this is exactly a statement where what happens to pair number 2, the state of pair number 2, depends on what happened at the step of pair 1. If at step 1 you got O, O, then you get epsilon 2 to correct the state. And if at the first step you get 1, 1, then you use epsilon 2 tilde to correct the state. That's exactly the, so this is just a way of writing a state which has the most general possible entanglement. So it's exactly the opposite of what you said. It's very important to make something which has all possible correlations. And that's exactly what was confusing people. They were thinking that when I do all these possible correlations, I have 2 to the n possible correlation terms. So even if each term is very small, I can make such a big change that overall I can bring the page curve down. And so the point that you can't do that is not obvious, and that's why you have to go through this theorem and you have to prove it.
And then I just wanted to double check something which you said earlier, which is, would you say then that the only way to solve this is to have a magical phenomenon where the interior particles come out? Or
Yes, so now there are 2 options to solve it. Given this theorem, the solutions become very sharp. Either you say that you don't have this at leading order, you make epsilon order 1. Okay, if epsilon is order 1, you can fix it. What does epsilon order 1 mean? Epsilon order 1 means that you are not close to the vacuum, you have just some complete mess there, you don't have anything like the Hawking process at all. So that's what the fuzzball does. It just makes it like a piece of coal and then it's all normal. And so in the string theory, the calculator suggests we are getting fuzzballs, and so you say that's the answer and then you're done. So that's one way of solving it. And then the other way is that you break the assumption of the theorem. That is, at the next step, even though you had step 0 out and 1 out, the out state is changed automatically by something non-local. And so even though the particles were emitted before and they were sitting out there, you magically go and change them at later times, and the spin keeps changing because of some non-local interaction with the black hole. You can write the non-local interaction in many ways. You can say this particle itself came out, or this particle influenced that particle. You can make many toy models, but that's the way you have to change it. Yes.
So when this particle comes out, what goes wrong with the third possibility of like small radiative effects which change the state? So you start out with 1, 1, then epsilon is small, but let's say at the next one you have like a radiative correction, it can be soft or something else. What goes wrong with turning that effective epsilon from small to large, just as pure radiative correction?
So you mean make the epsilon 2 as becoming big?
Now you don't just have the pairs, but you have a pair plus radiative effects from gravity or some other things. Like your background is fluctuating as well, right? And you have like memory effects and things like that, which show up when particles are being emitted.
So I don't think that that will do anything for the following reason, because we are talking about entanglement. And so what happens is that suppose you take a particle, suppose I have a particle here and it's going out. It's, let's say, particle number 1 out. It's going out. Okay. And now suppose as it's going out, at this step, it sort of becomes a mixture of 3 particles. It just does that. Okay. And this guy was entangled with somebody here with some entanglement. Okay. That entanglement doesn't change. It's very important that if you have 2 systems which entangle with each other, suppose I have a box with something, you have a box with something, and we have an entanglement of, let's say, log 2 between us. Now I check my state and I do any unitary process on it, but not to do with you, just in me, any unitary process. And you take your state and you do any unitary process on it. The entanglement between me and you will remain log 2. So that's the theorem. Only if you make an operation which is correlating me and you, like a non-local interaction between me and you, can our mutual entanglement ever change? And the reason is very simple. If you had an electron spin up and spin down, suppose you want a singlet, up, down, minus, down, up. And I say, I just flip my electron, up to down, down to up. Now the state becomes up, up, minus, down, down. It's a different state. But it has the same entanglement. Still, there are 2 pieces in the sum. So it doesn't matter what I do to my guy, I can't change my entanglement with you. So I can certainly do anything to this particle. In fact, the particle as it goes out, it may bump into other particles there. 2 particles which both come out can collide with each other, like Schmidt was saying. But it doesn't change the entanglement of what is out here with what is left behind there. And that's very important. When 2 things separate, then the entanglement can never change unless they interact again. And that's where it needs the non-local effect. So it's good. I mean, all these questions are very helpful because now it tells that with the small correction theorem, the Hawking problem is completely serious. That there is nothing, it's not like Hawking made some kind of approximation which was not good. Any approximation you make to Hawking will not change what Hawking was saying. And so now you only have 2 solutions possible. You can either have fuzzballs which means that you don't have the approximate black hole. So this completely changed, and then epsilon is order 1 and you've changed everything. So that's one answer. Or you have long distance non-locality, and I'll talk a little bit more about what you actually need. And that means the black hole is still like this, but there are sort of magical effects to long distances that go and they change the spins of things, or they do something, or they put particles there, or they do something like that. You have to have some non-local effects. So these things I'll put under the title of wormholes, because when people talk about these things, they often talk about wormholes. And so that's the other possibility. But there is no third possibility, because the small correction theorem doesn't allow any gentle, sudden, subtle changes to the problem, which hides the solution. I mean, you either have to sharply change one thing or sharply change the other thing, and but you can't just get around with saying that some small effect got missed somewhere and that can fix the problem. Okay. No, the theorem doesn't say that. Theorem just says you need a large correction. But to see what the correction is, of course, you need some particular theory. If you take string theory and start trying to find something, you find that you get these fuzzballs, which obviously have a large correction. They don't have a horizon. If you had some other theory and that you could get a big correction, well, that's fine. The theorem doesn't have anything to say about it. But in string theory, since you just get fuzzballs, you have to say, well, that's the answer there. Okay, do people want to take a break? Is 11:10? Okay, we can break for 5 minutes and come back. Yeah. Okay, good. I'll just start again now. So let's see where we had reached in our discussion. So we had seen that the small correction theorem tells us that we have two sharp possibilities. One is that you completely change the structure of the black hole. You can make it like a piece of coal or a star. And then, of course, there is no puzzle because there's no horizon. There's no place to have negative energy particles. You don't get radiation by the Hawking process. You get it by the normal radiation from the surface kind of process. And then the page curve will come down with no difficulty. And the other possibility is that you keep trying to keep the old picture of the black hole, but then you have some kind of long distance non-locality. And we want to talk a little bit about each of these things now. So the first thing that people tried to do was not this. They tried to look at this one, and they tried to make a statement about this, and they made what I'll call a claim or a suggestion. I will tell you what the suggestion is, but turns out the suggestion is not true. So that's why I'm calling it quotes, claim in quotes. It will turn out it's not true. And that's again something which can be proved, but it was at least a natural thing to think about. So what was that thing? And so faced with this problem, with the small corrections, then people said, okay, let's agree to the following thing, that in the exact description, the black hole really is a fuzzball. So if you actually write down the full quantum gravity wave functional, near the horizon, it's not the vacuum, there's no horizon, it's all just like a piece of coal. I'll just draw it like that. So let's agree they're all fuzzballs. So people started saying that maybe they're all fuzzballs. But then there is a low energy effective description. So if you only look at low energies in this fuzzball, but not the full detailed Planck scale structure. So here this will be having some kind of detailed Planck scale structure, right? Because everything is very messy and Planck scale everywhere. So it's a Planck scale structure. If it's got some low energy effective description, it will still look approximately like this kind of semi-classical black hole. So if that were true, then again, everybody could be happy. You could be happy because you solved the puzzle. The actual radiation comes out from the exact description. And so the page curve will actually go up and come down. And then if you want to think about what happened with the classical intuition, well, that classical intuition normally applies to low energy effects. And so if you take a low energy approximation of this, suppose it looks like this, then everybody could be happy. Okay. It turns out this is not possible. And so because this was a pretty common misconception, I just want to sort of address this. And why is this not possible? Normally, we do have a belief that you can take something very complicated, and at low energies, it looks like something simple. So for example, if you take the air in this room, in the exact description, you have like little atoms in various places, pretty complicated to describe that state. Okay. But then if you go to the long wavelength description, it's just like a fluid, and you can just make like sound waves in it. And then you don't even need to know where all the atoms are. Wherever the atoms are, the sound waves just go at some speed of sound, and there's nothing more to know. So that low energy, long wavelength description as collective mode, which gives the sound waves, that would be like this picture, and the accurate detailed description of where all the atoms are, that would be like this picture. So because it works for sound waves in the room, why can't it work for the black hole? So let's first see why it fails, and then go and see why the intuition behind it also failed. So reason this argument fails, again, has something to do with the small correction theorem. You can adapt the small correction theorem, and you can make something called the effective small correction theorem. Which was proved a few years after that. And the reason it's called the effective small correction theorem is that it says that even if you take something complicated and you say this emerges only as an effective description of this. So in the original small correction theorem, we were saying that the actual black hole is like this plus small correction. Now we're saying the actual black hole is pretty messy, but at low energy it looks like this plus small correction. Approximately like this, I already wrote an approximation sign, approximately like this, small corrections. So that's why it's a slightly different kind of question. But you can actually reduce it to the small correction theorem very quickly, and then you can prove this is also not possible, and that's why it's called the effective small correction theorem. As the logic is very simple. Suppose this was possible. Then let's look at the dynamics in this description. So in this description, you will actually get a pair of emitted particles, because that's all low energy effect. Hawking radiation, you just have low energy modes, and you look at low energy modes, and you will get the effects. Now that's not the exact description, because this is only approximate, right? So the actual modes you get will be the Hawking process, which gave you 0 in, 0 out, plus 1 in, 1 out. That was the Hawking answer. And then because it's only approximate, you'll have this plus delta psi. The only difference is that these are not the actual modes. These are the approximate low energy modes. I could write semi-classical here. Semi-classical, 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 semi-classical. They're not the exact modes, they're semi-classical modes. So it's not the same as what I was writing in the small correction theorem. In the low energy modes, it will be like that, and there could be a small correction. So let's allow that also. But now the problem is that this guy is supposed to be an approximation to the exact dynamics. Okay, because this guy, for the wavelengths under consideration, because there were long wavelength modes for the Hawking radiation, this guy is approximately this. Okay. So now you see all these small correction, the semi-classical guy, you can write it as O in exact plus a small delta psi. So can you see that if the semi-classical guy was an approximation to the exact guy, you can put it as the exact guy plus something that could always be some small error. And so you could map it to the exact, everything exact, and you'll get some different small correction. Okay, and then in one more step, you end up proving that because in the semi-classical description, the page curve was always going up, because here the Hawking pair, the page curve goes up. So that nobody argues about. Hawking argument goes up. Because you can relate this to the exact theorem with a small correction there, the difference, the approximate, this is small, the exact guy has to keep going up. If there's a semi-classical, this is the exact. So it doesn't take too much effort to prove that if the semi-classical description was like a normal black hole, if this was a low energy description, this would have normal Hawking pair creation, even though they are semi-classical modes and not the exact modes. And because in this, the page curve would keep going up, then you can relate it to the exact, because the exact has to be close to this for these particular modes. And then you go through all the small epsilons and deltas and you put them in, and you find the exact also has to keep going up. That means the exact guy could not have been having a normal page curve, which is what people were hoping. So it can't be that the exact guy lies like a piece of coal and the page curve comes down, and then it has a semi-classical description where, of course, you get Hawking pairs and the page curve goes up. Okay, so that's very funny. How come this whole idea that you can have something very complicated and at low energies, long wavelengths like in sound, it looks very simple? Why didn't that argument work here? And the reason is actually very interesting. If you look at the actual Hawking radiation which comes out of this black hole, so let's write the exact description first. This is the exact Hawking radiation. So here, in the exact description, these photons are coming out. Let's follow those photons back. So they have some wavelength like this. As I follow them closer back to where they started from this exact description, because of blue shifting, their wavelength is actually smaller. So I guess people are familiar with this. As you come closer to the horizon, the wavelength is actually smaller. And if you take a Hawking photon, which will have a wavelength of order r at infinity. R is the radius of the black hole. If it has that much wavelength there, by the time it comes to the surface of this guy, its wavelength becomes order L Planck. By the time you come within the Planck distance of the horizon, if you follow Hawking quantum back to that place, it actually becomes order Planck wavelength. And so really what is happening is that if you look at the messy Planck scale structure here, this guy, messy Planck scale structure, the actual emission that is happening from here is actually not of long wavelength modes. The physics that you actually need inside the fuzzball is not long wavelength modes. You're not looking at collective modes on the fuzzball like this. You're looking at modes which have wavelength of the order of the Hawking scale, order of the Planck scale. And those guys come out of this, and then they slowly redshift, and they become the Hawking radiation at infinity. But if you have something which has structure at the Planck scale like this, and it's trying to emit modes from in between, these modes carry all the information about where all these dots are. That's how the Hawking radiation carries the information. If I had a different set of structure in here, I'll emit completely different things from here. So that's how the Hawking radiation carries the information out. It's not seeing some general, overall, completely smooth average distribution. And that's why we could already see from this theorem that this kind of thing wasn't possible. If you could really map this to this and get the low energy approximation, and if the Hawking radiation was actually a low energy phenomena coming out of long wavelength collective modes, it couldn't have carried any information. The reason it carries information is that it actually starts off as Planck length objects. It sees fully the structure of this. So the analogy you should really think about is that if I gave you a piece of glass, and the atoms in the glass can be various places, if you look at long wavelengths, let's say 1,000 angstroms, each atom is 1 angstrom, then the glass doesn't care where the atoms are. So if you're wearing spectacles, the light goes through without actually knowing where the atoms are. It goes through one set of glasses, it goes through another piece of glass, exactly the same way. But if you look at wavelengths which are of the order of 1 angstrom, okay, which is going in the X-ray domain there, okay, they will not go through glass, because one guy will go here, depending on a different piece of glass, it will go there. It just can't actually see the glass as one collective thing and actually go like this. Or in the case of sound, if you're looking at waves which are smaller than the inter-atomic spacing in the gas, then there's no smooth wave propagation. So in fact, this theorem just tells you this is easier to, so that was the actual reason that it doesn't work if you compare what's really happening and why you can't get a long range approximation. But this theorem is actually much simpler, because you can just don't even have to know the reason. If this was a semi-classical approximation was valid, it would have the Hawking problem, and because this is supposed to be close to this for the wavelengths of interest for the Hawking process, then you have exactly the same problem, that this guy will have to have a rising page curve, and so it could not actually represent a unitary evaporation. Okay, so now it tells you that the fuzzballs.
Unless what we could call a semi-classical approximation is not really the low energy limit of some microscopic theory.
So good. So let's try to see what that could be. So then, good. So I was going to come to that in a little while. What people started doing with this then was that they started wondering about whether they could make some other kind of low energy approximation. But you can see that in here, we haven't made any great assumptions about what a low energy approximation is, right? We have just said that any low energy approximation which gives the normal Hawking low energy approximation to give this picture of the black hole. If you draw a picture of a black hole like this, it has to mean something. And what has to mean is that in the standard black hole, if a scalar field around the horizon was satisfying box phi equal to 0, it means you should be able to make a patch around the horizon where the dynamics is box phi at least approximately equal to 0. If you don't have that, you haven't actually made the approximation. But that is all that is required for the effective small correction theorem. So if you go back and see when people started saying that there could be other kinds of defining low energy approximation which they could possibly make the page curve work, when you go back and see what is wrong with those papers, what you find is that they are not actually getting this dynamics at the horizon. So they actually don't get any dynamics at all. So when I'm talking about wormholes, I'll come back and say what the mistake in those papers were. They say that they have made a smooth horizon. So at any one time step, they'll try to write down some state on a good slice or whatever. But then if you go from one good slice to the next good slice, it doesn't actually have the dynamics of a smooth horizon. And that's the mistake in all of those papers, the A equals RB kind of papers and so on. Okay, so let's see where we are right now. The small correction theorem told us that any small changes will not solve the problem. You either completely change the structure like in fuzzballs, or you go to long distance non-locality, which I haven't talked about yet. And with fuzzballs, you will, if you have the fuzzball, You can't also say that some low energy guy will look like the normal black hole. You really have a piece of coal, and that's it. Okay, so all these theorems are just narrowing it down. They're just absolute, just mathematical theorems. So now they're telling you that either you have the fuzzball solution to the problem, the black hole like a piece of coal, the original guy is completely gone. We already saw that it could be gone because the size of the quantum gravity effects didn't have to be Planck length. It could be some n times Planck length. And that's what string theory seems to do, because when we make the bound states, it always goes up to the horizon, completely changes everything. And so that would be sort of the end of the puzzle. So the only thing we have got left is, what is long distance thing that people are talking about? So I'll take the remaining time and talk about that a little bit. Are there any questions on this so far? Yes.
So the case of fuzzball resolves the previous puzzle because you don't have horizon, and
Yes.
what's inside eventually comes out.
Yes.
So essentially, any model in which we don't really have a horizon could potentially be a solution. Doesn't have to.
Absolutely, absolutely.
So-
These
so-
theorems are only telling you that if you remove the horizon, the puzzle is gone.
Okay.
And if you don't remove the horizon, you cannot solve the puzzle. That's, in a way, that's what this is saying. Because if you have the horizon, you will get the pairs, and then any small change to that will not help you. So that's exactly what it is saying.
Okay.
Yeah,
But is
but
there a question
anything.
about time scale? Like the ingo, whenever you have a pair, the ingoing one goes inside towards the center, right? And then it has to come out later. But you need it to come out like before the page time, or it cannot.
So by and large, as far as the abstract mathematics is concerned, it just has to come out before the black hole disappears. But in practical terms, it has to come out around the page time or before, for the following reason. If you leave all the particles in there till the time the black hole is almost gone, then they cannot come out. And the reason they cannot come out is the same as the problem we had with the remnant scenario. When you have very little energy left, but you need to carry out a large number of bits of information, then with that small amount of energy, you need to produce a large number of particles. Then each of those particles has to be a very long wavelength, because each of them individually has a very low energy. And if you have very long wavelength particles, there's no way to emit one particle of this much wavelength, and the next one can't be emitted till this one is gone, and then the next one starts. Right? Because if you have two particles in the same place, if they are bosons, they carry only one bit of information, not two. So that's what is a long-lived remnant. So you always have long-lived remnant scenario. If you don't take them, start getting the bits out by page time, like in the argument, the toy model of coal, the photon went out, then after halfway point, the ash also went out. If I leave it till too long, I'll get a slow, long-lived remnant, and that will again have troubles with ADS-CFT. But the long-lived remnant is always possible. So then there will be no constraint in time. Yes.
As you explained, this fuzzball picture, due to the blue shift, there you are probing like this microscopic structure inside the fuzzball. So I'm wondering, like, the scale analysis that you performed earlier regarding a conventional black hole, the order of magnitude analysis, that still applies to the fuzzball case?
Yeah, so that's a very good question. I was planning to talk about it if I had time, which I'm not sure I have, but we can certainly talk about it separately. A very good question which can be asked with fuzzballs, which Mathur always used to ask me, that if you have fuzzballs and you want people to believe in fuzzballs, why then is the temperature and the entropy and everything given by the same answers which we got from the old picture of the black hole? So that's the way of asking the same question, because the temperature gives you the wavelength. Here there was only one length scale R, and here you seem to at least have Planck length also being relevant. So this could have had any other arbitrary temperature. And so we wrote a couple of papers 2 years ago where we showed that if you have any fuzzball whose size, so this is the radius 2m, and the fuzzball size, you normally expect to be only a few Planck lengths bigger than that. So let me take something like this. So what we showed was that if the distance, if you have any object like this, whose distance outside the horizon radius, let's call that distance epsilon, is less than m over m Planck to the half times L Planck. So if you have anything with a size smaller than this, of order of magnitude smaller than this. So certainly, just being Planck length outside would satisfy this condition. Then the temperature of this object has to be the Hawking temperature. And the entropy of this object has to be the Beckstein-Hawking entropy. And the radiation rate from the object has to be the Hawking radiation rate. So all the thermodynamic properties have to actually match. So anything which is sufficiently compact, compact means close to 2m, but no horizon, it cannot have an arbitrary temperature. Since you've asked it, let's actually go through how you prove such a thing. Okay. So it follows from the following logic. You actually start trying to make an object. Suppose you have an object, let's take this object here. These things are called exotic compact objects, they're called ECOs. I assume it's very compact, so the size of the object is very close to 2m. So 2m is here, but the object is just a little bit bigger. Let this be Planck length. So I have something only Planck length bigger. And then you have some object like this. You can think of it like a dense neutron star or something. Size is 2m plus Planck length. And you say, why can't it be at 0 temperature? Let's put it at temperature 0. That's not the Hawking temperature. So then my job is to show you that you can't have that. Okay, so how do you show that? So suppose you do that and you assume that temperature T of the ECO is equal to 0. Okay, so you look at the metric it produces. Outside here, you just have the Schwarzschild metric. Inside, we have no idea what's going on. We don't even know if a metric is a good description. It could be something very quantum gravitational. We don't care. But outside, it's Schwarzschild metric to a good approximation because it's just a quantum ball. And now let's look at all the quantum fields on it. So let's take a scalar field phi living out here. Okay. And then if this is at 0 temperature, you can compute something called the vacuum energy of phi, vacuum energy density, rho phi. Okay. So what's the vacuum energy density of rho phi? You just solve the quantum fields of phi. Just outside the ECO is just normal semi-classical physics. People have solved the vacuum energy for fields in any metric, particularly Schwarzschild metric, for a long time. In this particular case, it was all done by Candelas in 1980. But the answer in this case is rather obvious. If you look at the region outside here, the region very close to this thing is basically what's called Rindler space. So in Rindler space, the lowest energy possible, if you make a 0 temperature, you get the lowest possible state in Rindler space. What is the state of lowest energy in Rindler space? The lowest energy state will be the Rindler vacuum. Okay, so Rindler vacuum. What's the energy density of the Rindler vacuum? The Minkowski vacuum has 0 energy density, but the Rindler vacuum has negative energy density. Okay. So I'll just assume people know that for now, but if you want to know more details, we can talk over lunch. So Rindler vacuum has the rho negative. And how much is rho? If you go a distance s from this distance to m, so if I go out a distance s, then rho is 1 over s to the 4. Energy density has units of 1 over length to the 4, and so that's the natural scale. Okay, so it's a negative energy density right outside here. It's basically a Casimir effect kind of thing. You know, Casimir effect in quantum field is just, for parallel plates it's negative. Sort of a similar effect here. So let's try to find how much negative energy I have in a little Planck scale band here. Let's look at a little Planck scale region here. And because there's negative energy, let's see how much energy I have here. It's a negative energy here. And you find a negative energy coming from this vacuum Casimir energy is order of minus m. Okay, that's not a small amount. It's minus m. Okay. So now let's see how this whole object is going to be structured. I've made an object which from infinity has a mass of m. Okay, so the mass at infinity, so m at infinity has the value of m. Okay, I'm trying to describe a ECO of mass m. As I come closer here, so up to here I'll see mass m, but then here I have a band of energy, let's say minus m, a shell of energy with minus m. So how much is the mass of this guy? If the total mass at infinity is m, and this guy has mass minus m, the mass of this guy is 2m. Okay. Now let's see if there's something wrong with that. If I have this object, I don't know what's going on inside this guy, but this is a guy of mass 2m. And it's sitting inside a radius, which is 2m plus epsilon. Now there's something very wrong with that, because an object of mass 2m, its Schwarzschild radius is 4m. So if I just look at what is happening here, this guy is sitting way inside its own horizon. Okay. And so the light cones just outside here are all turning inwards. If something is way inside its own horizon, you remember the discussion we had right in the first this part of our discussion yesterday? If you're way inside your own horizon, you can't sit there because you have to keep crushing in. That means this ECO just can't sit here. And so that's the reason you can never actually have a zero temperature guy, which is very compact. So what can you do? Well, if you heat up the guy a little bit, then here you have the negative Casimir energy, but there'll also be thermal energy from all the photons here. Basically, you take Rindler space and you keep adding energy till it gets to the like locally Minkowski space. At that time, the energy here becomes zero. And at that time, the whole balance fits again. So this is a very schematic argument. But what you technically do is you take the whole Oppenheimer-Volkoff equation used for a star. And in the energy balance, you put in the Casimir energy, the vacuum energy of all the fields that you have. And when you to solve that equation, you find that if this is true, the object is sufficiently compact, there's no solution. Unless the energy that you have has the correct amount of temperature to become the Hawking temperature. And once the temperatures match, you can use thermodynamics TdS equals dE. The entropy has to match and the radiation rate match. You can show everything from there. So it's a very curious result because it tells you that very compact fuzzball, which is what we expect the fuzzballs to be, just a Planck length or so outside the horizon. For them, the temperature and the thermodynamics is not arbitrary. You can just prove that if those guys exist, this doesn't tell you those guys exist. It tells you if an ECO exists, which is very compact, it must have the same thermodynamics as the black hole. But the answer is actually rather dramatic because it tells you all this black hole thermodynamics that we were used to, this particular value of T and S and so on that Fleming showed us yesterday, it doesn't actually come because there's a horizon. We thought it came because of a horizon because Hawking radiation came from the horizon and then we got a temperature radiation from there and we got the entropy factor fixed from the temperature and all that. So it looked like it was something to do with the horizon, but this argument shows you that it actually has nothing to do with the horizon. You just can't have a compact object, even if it has no horizon, at any other temperature. It has to have that temperature. And the closer this guy is, the smaller the epsilon is, the more better this approximation is. It gets closer and closer to that from the Oppenheimer-Volkoff equation. Okay, so let me just remind myself. Very important. You have a very large blue shift. So the picture of the fuzzball is that you have objects with very large blue shift. And in fact, that's how we prove this. If you assume for the ECO that you have a very large blue shift on the surface and solve the Oppenheimer-Volkoff equation, you'll find there's no solution in this domain. That's what you do. Otherwise, you don't know how to say it's compact because there's no horizon. But this, you actually state in terms of blue shift. Yes.
Can you say again what's the definition of a fuzzball? I think I missed it.
So the definition of a fuzzball for the purposes of the information paradox, so there are two sides to it. For the information paradox, the definition is just something which doesn't have a horizon. So a normal black hole you define as something which will have a whole region around 2m where the local physics is like empty space like this room. If you have anything else, let's just call it a fuzzball. Okay. That's the definition. But then the other half of the issue, of course, is that in string theory, you can actually go and construct the actual microstates of the black hole. Mm-hmm. And then you find they're of this kind. They're not a black hole. They are this messy. And so in string theory, you would say the fuzzball is actually like this because you can actually give the state. But more abstractly, even if you had some other theory and you just created something which was more like a planet but did not have a horizon, it would be like a fuzzball for the purpose of all the arguments. And
Can I say not a horizon of the GR type, but it can have a horizon, let's say like a quantum horizon with like a scratch horizon. That kind of thing is also what could be realization of your fuzzball definition.
So stretched horizon is sort of a more formal concept. It just is an imaginary surface you put outside the object, right?
Yeah, but suppose you can make it alive, make it dynamical, make it a quantum object. That would also be acceptable.
So the important thing for me would be, so that the part inside. So even though I was talking about it being like smooth across on both sides, the important thing is the inside part. Because a fuzzball is something which doesn't have any place where you can have negative energy. See, the whole black hole puzzle started because in the normal black hole, you can go inside the horizon and a particle can have net negative energy. That made the vacuum unstable and created all the problems, right? So if you just don't have any place where you can go in and get negative energy, then it's a fuzzball. That's you can call that the definition.
Perhaps I can I can give an example on Thursday, alternative to the
Yes.
string theory example with a matrix model construction of what could be called fuzzball in your classification. I will do that on Thursday.
Yeah, if you could make anything in any theory which doesn't have any place with negative energy, so that it's more like a planet or a star. In this context, I would just call it a fuzzball. But as I was saying, because the thing came up from the string theory side, because the actual things we got, usually people use the word fuzzball to refer to what we actually got in string theory. But because we're talking about information paradox issues and when you have the page curve going up and when it's not going up, I would like to use the word fuzzball for anything which doesn't have that negative energy in place. Yeah. Yeah, yes.
So you want a large blue shape, but no place, no empty space where it becomes infinite.
Yeah, so no empty space where it becomes infinite. But okay, so no space where so infinite, just as you go past the point becomes infinite, you get negative energy, right? Becomes infinite at the horizon.
Yeah.
It's a negative energy which you don't want.
That's right.
Right.
Yeah.
Right. That's right.
No, I mean that if it has to become negative energy, it has to really become infinite somewhere, and then that place cannot have just the empty space.
That's right, semi-classical physics. So that's right. So that's exactly what we do. We say that we define the ECO as being a place up to which we don't know anything, and outside is semi-classical physics. So we have to define the boundary of the ECO first to say what do you mean by be compact. So you define the boundary of the ECO as being where semi-classical physics holds up to there, and at the point where semi-classical physics still holds, if you can get a place where the redshift Z is much bigger than 1, let's call that a high redshift object. And then that place, if it satisfies this from the place where the horizon would be for that much mass, you say it is extremely compact. And then this is the answer. That's actually the technical way you do it.
The classical physics wouldn't differ much. Like, if I just
No, the classical is the same.
normal mode and usual
No.
things people associate with black holes.
It's the vacuum energy, but that's the same vacuum energy that you need to use at the vacuum, the quantum field, which you need to use for the Hawking effect. So if you don't even use,
Not quantum, just regular classical.
then there's no difference.
That doesn't care about whether it's really a horizon. That's what I'm saying.
You mean outside part,
Yeah.
like this versus this. In this region, there's no difference.
You observe like bring down most of people say.
Yes.
Bring down most. This would also have.
It's also, absolutely. It's all the same outside, exactly. Just one sec, there was a hand up there, let me take that, yeah.
So in these first 4 pictures, I mean, can we use this low energy effective description to describe, for example, collapsing formation process or accretion process?
So that's the very important question which I was going to talk about at some point. I may not have time now, but maybe we can catch up more in discussion. But maybe let me use the remaining time to say something about that. So as I said, the reason people were worried about this in the beginning, the fuzzball, is they were saying if quantum gravity only acts on the Planck length, how can it change things all the way up to the horizon? And we said that itself was not a good argument because the size of quantum gravity effects, they can be order LP, but they can also be n times LP or n to some power times LP, where there's a number of particles in there. And so you could easily get something going up to the horizon. This itself was not a good argument for anything. But there is a much stronger argument to worry about fuzzballs. And that is that if you look at the process of formation of the fuzzball, then it looks like when the star was collapsing, the picture we drew yesterday on the blackboard. So let me draw that picture again. So we drew a shell which was sort of collapsing like this, and then it sort of goes in and then becomes a singularity. So all this is just low energy stuff. And so where in this argument do you say that it should not become like this, but instead here it should become like a fuzzball? So that's what we are trying to do, right? We are saying a shell is collapsing, it should become a fuzzball and not continue to go in. But this is a dynamical process, and everywhere that this thing is happening, all here, all the curvatures are low. So if I add the curvature scalar R, it is much less than 1 over L Planck square. And so why are big corrections arising? Okay. And so you need to find some way of making it possible that you have a theory where even though the curvatures don't become big in this region, instead of getting the normal singularity, you instead get the fuzzball. So the question would be, how do you create the fuzzball? Because all the calculations of fuzzballs we are actually doing in string theory, we just take the time independent state. We join some brains, make a bound state and look at the nature of the state, and we see the state is not small, it's as big as the horizon. Those are time independent configurations. But if you cannot actually produce them in the dynamical process, you'd have a funny situation. All the time independent ones look like this, but the dynamical process is taking you to something else. And so the question is, what goes wrong in the dynamical process? So what you really need to do, because we still would like to believe in locality, because in string theory there are no non-local effects as far as I know. The question is, can you actually make a Hamiltonian which is completely local, and in which, even in a region where all the curvatures are low, if you ever try to make a horizon, curvature is still low at the horizon, but if you're just reaching a point of high redshift, something new happens even though the curvatures are low. And there are no non-local effects because everything is local in the Hamiltonian. And so what I've been doing recently is making toy models of the quantum gravity vacuum where this actually happens. So we can't prove that's the nature of the vacuum, but you need to be able to prove that it's at least possible to imagine a structure of the vacuum of quantum gravity where you will actually, at that point of making a horizon, something new happens even though the Hamiltonian is completely local. So there's some papers I have recently out, something I wrote just about a week or so ago, which has such a toy model. So I make the models in terms of condensed matter things. You can do something with the toric code model, slightly modify that and get something with a local Hamiltonian, but where if you change things over a big region, but softly everywhere, you get a phase transition. So if it wasn't actually possible to make a local model which will do this, you still haven't solved anything because you still have a puzzle. Okay, and so I think it was very important that there at least can be a model of the vacuum where locality is maintained and you can still get fuzzballs without breaking either locality or causality, or curvatures ever becoming high in the region of interest. And so there is a possible model to do that. So I'm not going to describe the model right now, but we can talk about it privately if anybody is interested. But that's a very important question. If you don't solve that, you still haven't solved the puzzle. Did you have a hand up?
Yeah. So in this scenario where actually the quantum effects are becoming very large.
In the center.
So the curvatures are very small.
Oh, you mean in this? Yeah, when you do this, yes, yes.
What equations are you going to solve? I mean, you're not going to solve Einstein equations anymore, right?
Yeah, yeah. So we are not trying to actually write down the actual equations which give the fuzzballs or anything.
Just conceptual. What should I do instead of Oppenheimer wormhole?
Yeah. So roughly the way it happens is the following. Suppose you were looking at Hawking radiation, but you didn't know about Hawking radiation. So before that, then people said nothing can come out of the black hole. The light cones are going in, there's nothing to radiate, so why should anything come out? Then you look at the vacuum fluctuations, and you find that's where the radiation was hiding. Because the vacuum fluctuations, they were just the vacuum, but then when you stretch the space, like we drew in the pictures yesterday, the vacuum fluctuations become real particles, and then you see the radiation. Okay. So the whole key is the nature of vacuum fluctuations. So what we are going to actually say is that there are more vacuum fluctuations which are not just the Gaussian fluctuations of a quantum field that we are normally used to. The normal Gaussian fluctuations of a quantum field give Hawking radiation effects. So we know that. But the Planck scale structures in the vacuum have other kind of vacuum structures, which is what we describe in this paper, in this model. And when you reach a situation where the redshift in one region is high compared to another region, those vacuum fluctuations react and turn into something like on-shell fuzzballs. So if you like, it's a kind of much bigger version of the Hawking process, where instead of just creating low energy particle pairs out of the vacuum, in certain situations you nucleate this entire fuzzballs. So what you got to make sure is that the vacuum structure is such. So if Hawking didn't know about the vacuum structure of this Gaussian quantum fields, there would be no Hawking radiation. And so you need to make a vacuum structure such that it responds to differential redshift and nucleate these particular.
And then you're going to use this as an input to the right-hand side of Einstein equations?
No, I think the Einstein equation part, so we are not going to doing anything that sophisticated. We are simply saying that,
No, I mean, if
yeah.
you were, I mean, what would you have done?
So I think you wouldn't do it doing Hawking, no, you can't do that because even the Hawking radiation doesn't come that way.
Yeah.
Because you can't write anything local correction to the classical equation to say that you got a Hawking pair. The Hawking pair actually sees the entire geometry on the scale of R, and the entire mode on the scale of R changes to a different mode which now has an occupation number, right? So here also the same thing happens. Even though the vacuum is local, it actually has correlations which actually stretch across all scales in a power law form. And so the key point is that normally you always expect a lot of bubbling at the Planck scale. Everyone draws a picture where you have space-time foam at the Planck scale. But what is the correlation length of that space-time foam? So normally you think that those Planck bubbles will also, the correlation will also fall off at the Planck length. It's just some Planck bubbling, so that's the only scale. But suppose you change that and you say the Planck scale bubbling, their correlations fall off as a power law. So you're like at a second order phase transition. That's all you have to do. With that, and appropriate follow-up of these correlations, you can make a picture of the vacuum, which when you're actually in this situation, and you reach this big redshift between here and here, which is becoming much larger than 1, will actually start nucleating these Planck bubbles into on-shell bubbles rather than vacuum bubbles. So that's the structure. So you're trying to make this Planck scale bubbling of the vacuum, because the fuzzballs are basically structures of where Planck scale bubbles join up in a certain way. Okay, so that's where the initial motivation comes. So you really need to make the Planck scale bubbles become on-shell when you get a big differential redshift between the horizon and some other place. So that's the key. So Hawking was playing with these long low energy wavelength modes, and the Gaussian fluctuation of the vacuum was enough, and the quantum gravity wasn't really coming in. But if you have look at the structure of the quantum gravitational vacuum and you make it appropriate, then you somehow discharge into that in this situation. So that was the model we made. But so Ajay, just to emphasize what question we are solving here, you need to actually be able to create the fuzzballs and in a place where the curvatures are all low. And so you need to structure the quantum gravitational vacuum at the Planck scale, which is not involved in all our discussions of Hawking radiation, because that's only long wavelength modes, such that fuzzballs actually form so that you can smoothly go into what you want as the states of the black hole, rather than again getting trapped in the information puzzle. Question?
For 30 years that black holes are bound in string theory. Black holes are just complicated bound states of the extended objects, the brains and everything. So I would have said that the equations you're solving are the equations of, it's maybe not GR coupled to that kind of matter. It's more like, you know, the kind of thing you get in ADS CFT. It's more like the brain dynamics. It subsumes gravitational dynamics within it, but is more than that.
More pedestrian. Like, I mean, what do I mean by forming a fuzzball? I can understand the quantum state evolving into some other quantum state.
Yeah.
But here, if I want to call fuzzball as an example of ECO, what should I be looking for?
Yeah, so that I can say a little more precisely, because fuzzballs are, in the simplest examples, made out of KK monopoles joined by S2s between them carrying fluxes. So the toy models I make, you simply have the Planck scale structures are like KK monopoles, like you can make local excitations, and you simply want a nucleation of these monopoles to happen when you get a big differential redshift between two places. So, and then,
But again, that's
solve some equation, right? That was my question.
yeah, so it's a little bit like the Hawking radiation again, because let me say a little bit more about how it happens. So if you look at these models which come out of StatMech, which are all in the category of what are called resonance valence bond, RVB models or dimer models or toric code models, they're completely local Hamiltonians, but they have the property that suppose the spin on one bond is, let's say, up. Then on some bond coming out of that site again, it must also be up. You can't have only one bond up radiating from here and all the other ones down. If this is up, at least one of the other guys must also be up. In that case, all the spins which are up, they form like loops, closed loops. Okay? If you actually make something which is not a closed loop but just ends somewhere, that's actually called a monopole and costs extra energy. So you can have a complete local Hamiltonian which has this structure. So let's assume we just take this kind of local Hamiltonian also for our quantum gravity vacuum.
So it's not a Schrodinger equation.
Ultimately, everything is a Schrodinger equation of these monopoles.
Is there any procedure by which that Schrodinger equation becomes the dynamical equations of gravitational collapse?
No, I'm not doing that. Oh, yeah.
That was exactly it.
No. So I'm actually doing something less than that. I'm simply saying I want to make a model of the gravitational vacuum, but at every place I have just some rules like this where the Planck scale bubbles are basically have to follow some rules like this. The vacuum is sort of like the vacuum in the toric code model. But then if you actually say that in this region there's a higher redshift, what happens is you make these paths which go through this region cost you more energy. Okay, so that you can arrange easily with the local theory to do that. And then what happens is, at some point when the energy here becomes too much, it's cheaper for the path to simply end in a monopole here rather than to continue here. And you actually get a phase transition which is same as a percolation phase transition. If you make the paths more difficult to go in some region, there's a phase transition where they don't want to percolate here anymore. And then all these paths outside, they just end on monopoles here. Okay. So this was only like an existence proof that you can make a model of the vacuum in quantum gravity, which has only interactions at the Planck scale, but in which you only change things gently and not say something happens here, I want a monopole here. But if you just, in a percolation transition, if you just keep increasing the price of the bonds here a little bit, at some point as a phase transition, nobody wants to percolate there. And then you simply get monopoles forming at the boundary. But fuzzballs are basically a collection of monopoles that are joined to each other. So in that sense, you just mimic fuzzball formation. So this is just a toy model which says this is at least possible. Before there were models like this which I could convince myself are at least possible, it was actually a very puzzling question. If you can't ever make a fuzzball from a local theory, what are we even asking for? There's still a big gap. You can show the individual states of fuzzballs, but if you don't have a clear way of making them, or at least a possible way of making them, there's a big hole in the argument. But this, what we call the Vecro models, fills that hole. That's not to say that we can actually prove the quantum gravity model is like this, but I sort of feel that any model you try to make to solve the puzzle will basically be of this RVP kind. If you don't have this kind of loop structure, the loop could be a sheet, and there are all kinds of models you can make like this. They're all in the same universality class. But if you don't have these structures, I think you can't solve the problem. Okay, thank you. I'm a little bit out of time, but if there are any further questions, we can definitely talk over lunch, but we can also talk in the discussion session.